So, we will again continue the same thing, problems, and particularly based on the linear functionalization. The first problem is, suppose the space CAB, the space CAB we have already discussed, set of all continuous functions defined over the closed interval AB. Now, we are taking the C dash AB. C dash AB is the set of all, is the norm space of continuously differentiable functions defined on J, which is a closed interval AB, with norm defined by norm of x is maximum of mod x t, t belongs to J, plus maximum of mod of x prime t, where t belongs to J. So, the problem is, prove that the CAB, I will just write like this, prove that or show that the space C dash AB is the norm space of continuously differentiable functions on the closed interval AB with norm defined as this. Clear? So, this space is different from the CAB. CAB we are taking only the continuous functions defined over the closed interval AB, and in that case the norm was given in terms of the maximum mod x t, or maybe the integral form a to b x t dt. But here not only those continuous functions are there, even we are including those functions, means instead of taking those continuous functions for all the continuous functions, we are taking those continuous functions whose differentiation is also a continuous function, whose derivative is also a continuous function. So, set of all continuously differentiable functions, okay, is that is why we are adding this term also in order to get all the properties of the norms satisfied. If I do not put this term, you will see that all the condition of the norm space will not be satisfied. Okay. Let us see the first part. Norm is obviously greater than equal to 0, because each one is mod. So, and this is a continuous functions on CAB. So, obviously these things derivative etc. will give the non-negative quantity, mod of this is there, we get. Now, if it is 0, what happens? The right hand side of this expression is 0. So, maximum of x t is 0 and maximum of x prime t is 0. So, this will imply that x t will be 0, x prime t will be 0 for all t belonging to J, because once the maximum value is 0, then for all values of t it will be 0, modulus is given, okay, absolute value. Now, x t is 0 means x prime t 0 implies the function x must be a constant function, okay, and since first condition shows x t is 0, 0 is also constant. So, it can take the value only when x is 0. So, x must be identically 0. So, norm of x equal to 0 will imply x is equal to 0. Is it okay? So, I will write theta, clear, 0. Is it okay? So, Second condition, norm of x plus y is less than equal to norm x plus norm y. I think obviously it is true, is it not? So, I will not write this way. This is norm x plus norm y, one can obviously see. And similarly, the third condition, when alpha is a constant, then you are getting this is maximum of alpha x t, t belongs to j, plus maximum of alpha x prime t, this is alpha x prime t, and t belongs to j. So, we can take mod alpha outside and remaining thing is norm x. So, all the conditions of this are satisfied, therefore, it forms a norm space. Clear? Is it okay? So, and this space is interesting, it is very interesting space, and we will see many application, and you will see this type of space. Okay. Now, another problem, if f is a bounded linear functional on a complex normed space, complex normed space capital X, then each f bar is f bar, where f bar is a complex conjugate of f, is f bar bounded, is f bar linear, where f bar denotes the complex conjugate. F. F bar x means complex conjugate of f x. Okay? That is. So, what is given is f is a bounded linear functional on a complex norm space. It means when you take x, point in x, the f of x, that will be a linear function, that will be a scalar quantity and belongs to a complex set. So, we can talk about the conjugate of f. Now, the question is, in place of f, if I take the conjugate of the function and then operate on x, whether that function remains linear, remains bounded. Okay. So, first part is we claim f bar is bounded. Why? What is the condition of the boundedness? Because f is bounded linear functional. So, by definition, mod of f x is less than equal to norm f into norm of x. This is by definition. Clear? Now, I replace g, suppose g is equal to f bar. Okay. Now, we wanted to test whether this function is bounded or not, define on x. So, let us consider the mod of g x, that will be the same as the mod of f bar x. Okay. But this f bar x, because it is a conjugate value, that will be the same as the mod f x. So, we get mod f x, mod of z and mod of z bar will be the same. So, this will again less than equal to norm of f into norm of x, or this norm f you can just put it the star also bar, there is no problem. So, we can say this is less than equal to g into norm of x. So, it is bounded. Okay. Now, what about the linearity? The f bar, will it be linear? F bar is not linear. It means the condition of the linearity, that is f of alpha x plus beta y should be equal to alpha f x plus beta f by fails, or maybe one of the condition fails, because there are two conditions. One is f x plus y is equal to f x plus f y, another one f of alpha x is alpha times f x. So, if one of the condition fails, then you say f is not linear. So, I take f bar alpha x. Okay. Now, is it the same as alpha x conjugate? Basically, f bar means a function f defined on some point and then taking the conjugate, that is the f bar. So, alpha x function is defined and then taking conjugate, but f is linear. So, we can write alpha times of f x conjugate as f is linear. By the property of linearity, this alpha can come outside. Since alpha belongs to as a point in C, so when you take the conjugate of this, it will be equal to alpha conjugate into f bar. Clear? It means f bar of alpha x is not equal to alpha times f bar x. So, it is not linear. Okay. So, function f is bounded and linear, but the conjugate of this will remain bounded, but not linear. So, that is the interesting. You can find.
Sir, would you kindly repeat this thing?
Which one?
F bar alpha x.
F bar of alpha x. This is okay. Then we are not touching this one bar. We are applying the property of the linearity of f. F is linear, so alpha can be taken outside, and then this will be alpha bar into this bar. So, that is what. But actually we wanted the alpha times of f bar x if it is linear. So, it does not satisfy that condition, therefore, it is ceased to be a linear. Okay. So, this completes. And another example is, let f which is not equal to 0 be any linear functional on a vector space x, on a vector space x, and x naught any fixed element of x minus n f, where n f is the null space of f. Okay. So that any x, belonging to capital X has a unique representation as x equal to x naught plus alpha x naught plus y, where y belongs to n f. Let us see what is this. Okay. is be any non-linear f be any linear functional vector and x naught be any fixed element of x. So, x naught is given in x minus n f, it means the value of the function at a point x naught is not equal to 0. Clear? Achha, what we want is that we wanted to show that any element x has a unique representation of this form, okay, where alpha is a point in complex plane in the field of x, alpha belongs to the field of scalar of x and bi is a point of n f. Okay, this well. So, let us choose.
So, kindly tell us the definition of null space.
Okay. Null space is the set of those points, or we know the null space n f is the set of those point y such that f of y is 0. Okay. This is the null space for this. Okay. Now, if we take alpha to be x f x divided by f x naught. Suppose I take this alpha, okay, x be any point, and by I am choosing to be x minus alpha x naught, because x naught is given, x you are choosing an arbitrary point in x. So, these two things are known. Okay. If I take alpha in terms of f x and f x naught, this is also known, clear, because f is given, f is given. So, everything we can now pick up. If I construct the by as x minus alpha x naught, then what is the image of by under f? This is equal to f x minus f of alpha x naught, but f is linear. So, it can be as f x minus alpha times of f x naught as f is linear, clear, f is linear, but alpha we are choosing f x over f x naught. So, this entire thing will be 0 because alpha I have chosen to be f x over f x naught. Is it clear or not? It means the image of by under f is coming to be 0. So, this shows that y must be a point of n f. Okay. So, what we have proved is then any element x from here, x can be written as alpha x naught plus by. Any element x can be expressed in this form where by is a point in n f. Is it okay? But what we want is this representation should be unique also. Means we can express x in one and only one way in this way. Okay. It means if we have the two representation, then that representation will not give the two different values. That is, if I take x as a alpha x naught plus by 1, another representation x is alpha x naught plus by 2, then these things should not be the same. Okay. It will give the same value. Okay. So, to show the uniqueness, suppose it has two representations. Suppose x has two representation. One is x is alpha 1 x naught, alpha 1 x naught plus by 1. Okay. Another representation is alpha 2 x naught plus by 2. Suppose it has the two representation like this, where by 1 and by 2, these are the elements of n f, and alpha 1 alpha 2 belongs to the field of a scalar of this. Clear? Okay. So, from here we get alpha 1 x naught, it means we should have a contradiction, alpha equal to alpha 2 x naught plus by 2. Okay. Now, this will give alpha 1 minus alpha 2 x naught equal to by 2 minus by 1. Clear? Is it okay? Now, from here we conclude that alpha 1, okay, if by 1 and by 2 belongs to what? If alpha 1 is not equal to alpha 2, what happens? If alpha 1 is not equal to alpha 2, then what we get? We get x naught equal to 1 by alpha 1 minus alpha 2 by 2 minus by 1. But by 1 and by 2 are the point in null space, and null space, this is a vector space we have shown earlier. So, this element will be a point of NF, and this is nothing but a scalar. So, entire thing belongs to NF. So, what conclusion is? So, therefore, x naught point, the x naught point, this is an element of NF. Is it okay? But it is a contradiction to the fact that x naught belongs to x minus NF, because in the result, in this exam statement itself, x naught is any fixed point of x minus NF. So, x naught belongs to x, but not in NF, but here we are getting x naught belongs to the NF. So, a contradiction, and this contradiction is reached because our wrong assumption that x has a two different representation. It means this shows that x can be expressed only in the form of alpha x naught plus by. This by may be changed, no problem, but this alpha will remain because x naught is fixed. So, alpha of x naught will remain, then x linear combination with the elements of by. So, is unique, has unique representation. Okay, we get that. Means alpha must be so here, so alpha 1 should be equal to alpha 2. These must be the same. Okay, can you always? Is it correct? So this. Okay, then next. So that two linear functional f1 which is not equal to 0 and f2 which is also not equal to 0, the non-zero linear functional, which are defined on the same vector space capital X and have the same null space are proportional. So, this is what we want. Let us see how this works. So that the two linear functional f1 and f2 which are defined on the same vector space X have the same null space and have the same null space are proportional. It means f1 f2 x can be expressed as a constant times of the f1 x. then only, is it not? This we wanted to show. Now, prior to this we have proved one result, one example we have done, that if f is any non-zero linear functional, then any element x, and x naught is a fixed element of this, then any element x can have a unique representation like this. So, we will take advantage of this, okay, because f is giving to be non-zero, here f1 and f2 both are giving to be non-zero. So, we can take up one function, say f1 first, and then any element x can be expressed uniquely in this form alpha x naught by naught. So, let us take solution. So, by previous example, should I write this by previous example? Okay. We can say any element x, any element x belonging to capital X, is it not, has a unique representation in the form of x as some alpha x naught plus y, where y is an element of n f, and if you remember in derivation alpha is taking as f 1 x over f 1 x naught, is it not clear? So, any element x has a unique representation as this, where f 1 is not equal to 0, a linear functional on x. Okay. So, basically we are writing x to be f 1 x over f 1 x naught into x naught plus y. Okay.
So then this y will belong to nf1.
nf1, where y belongs to nf1. Is it okay? Now, what is given in the question? Two linear functionals are given, both are non-zero. I am picking up only one linear functional and applying the previous example and writing the expression x in terms of f1. Is it okay? Where this element belongs to y. But another condition is given, that f1 and f2 have the same null space. It means nf1 will be the same as nf2. Okay. So, the value of y under f2 must be 0. Okay. So, the value of y under f2 must be 0. That is, what is the value of this? Y is nothing but the x minus f1 x x naught into x naught. This must be 0. Is it okay? Or from here, can you say f2 x minus f1 x f1 x naught into f2 x naught is 0? Is it okay? Because f is linear, f2 is linear. What are the constant now value? f2 x is a variable, because x is variable. So, it will have a different value depending on x, but this has a fixed value, this has a fixed value. So, basically f2 x can be written as constant times of f1 x. So, this implies f2 x is equal to constant times k of f1 x. So, are they not proportional? So, f1 and f2 are proportional. Clear? It's a good example. So, this gives a conclusion here like this. Suppose on the vector space X or norm space X, if we are having the two different linear functional, then if their null space are the same, then they are proportional.
Sir, excuse me. What is the linear vector space?
Linear vector space.
How do you define a linear?
Actually, the vector space means the set X together with the operation addition and multiplication, then this is called the vector space, or sometimes we call the linear space. Okay. But linear vector space we mean when this addition and scalar multiplication they are jointly continuous, then space is said to be a linear vector space. Okay, linear vector space. For the vector space, the continuity of the addition and scalar multiplication is not required. Simply we test it whether it is closed with respect to the operation addition or the 5-fold property with the scalar multiplication or 5-fold property, then it is a linear space. Clear? But if on this structure, if I define some norm, okay, or some other operation in which the addition and scalar multiplication becomes continuous. For example, if I define the norm, then what happens? The norm becomes continuous with respect to addition as well as scalar multiplication. So, when the addition and scalar multiplication are jointly continuous, then such a structure we call it as a linear space. It means it should be a linear space, vector space, it should be a continuity and scalar multiplication must be jointly continuous. Okay.
So, how,
in fact,
do you call this continuous? Suppose
continuous we mean, I think this we have discussed last time. So, normally we say the non-linear space. When you say linear vector space, it has meaning, no meaning unless you use some norm. Okay, sir. So, when we say the non-linear space, non-linear space, it means it is a linear space, it is a norm space, okay. And then third is the addition and scalar multiplication are jointly continuous. Jointly continuous means if x n converges to x, y n converges to y, alpha n converges to alpha, then and beta n say converges to beta, then alpha n x n must go to alpha x dot product and x n plus y n must go to x plus y under the norm. Then we say this norm is a continuous function with respect to addition and scalar multiplication. That is the meaning is norm of x n plus y n minus x minus y must go to 0. Then and norm of alpha n x n minus alpha x must go to 0. So, with respect to addition and scalar multiplication it is continuous. So, if a structure which has addition, multiplication and some other suitable operation like norm, maybe a inner product like this, then only the concept of the norm linear space comes, okay, when the joint taken. Okay. So, but we are dealing only with the linear spaces or norm spaces. Jointly this will, in fact, this will lead to a concept of topological vector space. Okay, that is okay. Now, let us see then another example.
So, my question was regarding linear space. Why do you call a space linear?
Linear space to same as the vector space.
That means
Linear space, a linear space or be called a vector space, both are terminology same. It means as X is a set and two operation addition and scalar multiplication are given. If X plus is a abelian group, abelian group means it is closure, property is satisfied. Closure means if x1 belongs to x, x2 belongs to x, then x1 plus x2 must be in x. Closure property, okay. Then identity, associative property. Associative means x1 plus x2 plus x3 is x1 plus x2 plus x3, where x1, x2, x3 these are the elements of x. Okay. Then third is first, second, then identity for addition. There exists an element 0 belongs to x such that x plus 0 is 0 plus x equal to x, and this is true for every x belongs to x. Then we say that identity element with respect to the addition exists. Okay. And fourth is inverse corresponding to each x belonging to capital X, there exists minus x belongs to x such that x plus minus x equal to 0 equal to minus x plus x. Okay. Then this is called the additive inverse of x. Then abelian or commutative. Up to here 4 property, it is called a group. X plus is a group, and when you take another property commutative, that is if x 1 plus x 2 is the same as x 2 plus x 1, then where x 1 x 2 are any arbitrary element of x, then we say it satisfies the commutative property and structure is the abelian group. Okay. So, with respect to the first operation, x must be an abelian group. Then second one is, so this is the first A condition. So, there are 5 conditions are required to satisfied to be abelian. Now, B, x with respect to multiplication, this is a scalar multiplication, is a semi group. That is, if alpha belongs to the field K of scalars, x belongs to capital X, then alpha dot x must be a point of x. So, closure property, this is the closure property for scalar multiplication. Then alpha dot beta dot x, this will be equal to alpha dot beta dot x. Okay. Then alpha plus beta dot x is alpha dot x plus beta dot x. Okay. This is true. Then alpha dot x plus y is the same as alpha dot x plus alpha dot y. Then another property is 1, there exists 1. Okay. See, there exists a 1 belongs to x such that 1 dot x is equal to x for all x. Scalar multiplication, identity for multiplication. Okay. So, this property as a semi group, like so basically there are 10 property satisfied by this. Okay. So, these properties we call it as a semi group. Is it okay or not? Huh?
If these all properties are satisfied, then we call them vector space as linear vector space.
Huh? All the properties, yeah. Yes. Huh? Any vector space is linear has no meaning. Linear space is the same as the vector space.
It is termed as in book for this wavelet transform.
Huh?
I'm reading.
Huh?
That is termed as linear vector space.
Linear vector space is different than the linear space or the vector space. I told you.
Yeah, what is that actually?
Huh.
My question is referred to that only.
That just now I earlier told. When the operation addition and scalar multiplication, they are also connected with some other operation which is jointly continuous, then it is called the linear vector space. Okay. Now, maybe some books use the word linear space also as a linear vector space in some books, but normally we use the like Kreyszig here in this book linear space and linear vector space different concept, but in some books linear space and linear vector space they consider to be the same which satisfy this property. So, depending on the books. Okay.
When the first 3 properties are satisfied, then we call that vector space as linear vector space, but it must be linear space.
Yes, exactly.
Normed space and plus and this dot are jointly continuous.
Non-linear space. norm is there.
Yeah, norm. That is
Norm. Under the norm it is
linear
continuous.
space.
Yes.
It must be normed space.
And then jointly continuous.
Plus and
Then it is a non-linear space. But if the sum book is writing only the linear vector space, it means he is meaning with the linear space only. He means only the linear space. So you just check the book. What are these? Whether any okay, but whether any operation addition and scalar multiplication apart from this, any other operation he has taken?
So he has not defined vector space.
No, whether addition and multiplication, whatever the two operation, is there any third operation in that? If not, then it is the same as the linear space.
Sir, he was discussing this Fourier domain. I mean Fourier.
So he means only the linear space. Okay, that's one. Clear? So this okay? Okay. So we were discussing some problems. Okay. Now let's take this problem. Okay. If y is another problem on the linear, if y is a subspace of a vector space X and F is a linear functional on X such that f y is not the whole scalar field, is not the whole scalar field K, is not the whole scalar field of K. So that field of X, so that f y is 0 for all y belongs to capital Y. All y belongs to capital Y. So what is this? If y is a subspace of a vector space, this is our vector space X over the field of scalars, say K. K is the field of scalar. Y is a subspace of this vector space and F is a linear functional defined on X. Then it will have the image f of y. Each element of y will be mapped. So this is the f of y. Okay. Now this is a linear function, so this will be the set of scalars, basically scalars belonging to K. Now what he says is, if f I y is not equal to K, that is, it is a subset of proper subset of K, then f y will be 0 for all y belongs to this. Y is a subspace of the vector space and f is a linear functional on X such that f y is not the whole scalar field of X. That is, image of y under F is not equal to K. There are some more scalars are available, okay, which are not in f y. Then what he says is that the value of element y under F should be 0. That image of such a function f, okay, will take all the points elements of y to be 0. Okay. So that is what is. Let us take this, let us see this. Suppose for some point it is not 0. Okay. So suppose y naught is a point in y such that f of y naught is say gamma which is not equal to 0. Okay. Suppose then we should read a contradiction. Okay. Now, pick up alpha, a scalar which is equal to alpha by gamma into f of y naught, because f y naught is gamma. So, this cancel and alpha equal to this. Okay. Now, f is what? F is linear, this is constant. So, it can be written as f of alpha by gamma into y naught, because f is linear. Okay. Now, since y naught is a point in y is a subspace, capital Y is a subspace. So, this will be a point of y. So, if it is the point of y, then each element must belongs to f of y. Okay. This belongs to f of y. If you remember, if X is a finite dimensional case, all this we know, a matrix A, which is a matrix Aij of order m cross n, then this represents a transformation from Rn to Rm. Remember, and this is a linear mapping, linear transformation, in fact linear functional transformation from this matrix to, okay, and bounded also, bounded linear transformation, or operators you can say transformation or operator. And how to define this one is Aij and then xij sigma j 1 to n. This is our eta j. Okay. Then this elements xn where x is equal to xij j equal to 1 to infinity and y equal to eta I, sorry this is eta I, eta I is 1 to n and 1 to n, is it not? So, this is our eta I. It means it can transfer the elements of x n to the elements of y n under this transformation, and we write a x equal to y. Okay. Now, this is the case when A is finite dimensional. Similar case we can extend to the infinite dimensional. Okay. If there is a matrix A is a matrix, suppose A is a matrix Aij of order infinite dimensional, where I is varies from 1 to infinity, j is varies from 1 to infinity. Okay. And x and y, these are the spaces. X is xi1, xi2 and so on, is an infinite dimensional space. Y is eta 1, eta 2 and so on, is again an infinite dimensional case. Then how will you operate from x to y? How to define? Finite dimensional case is okay, because this series is finite, convergent, therefore, the corresponding will be the convergent. So, this definition leads to the concept of matrix transformation. How did we define? In a similar way, what we do is we consider this sequence sigma Aij xij j equal to 1 to infinity. Okay. Now, this sequence we call it as a axi. Okay. Axi, because x1 x2 xn are there na. So, a of xi. Now, this elements, if this is convergent for each I, this sequence converges for each I, because this is infinite series, I is 1 to and so on. So, if this series converges, series sigma Aij xij j equal to 1 to infinity converges for each I. Okay. And the sequence Axi is an element of y. Okay. Is an, suppose it is L infinity, so sup of this must be there. If it is L1, sigma of this thing must be there. If this is in y, then we say A maps x into y, or A is a matrix transformation from x to y, and we denote this thing as A belongs to x comma y. You follow me? Clear? Because this is a double summation Aij, and I is not finite, and this j is also not finite. So, for each I, suppose I take A1, then A1j, this will give a infinite series. So, this series must be convergent for 1, A2, A3 and so on, Ai equal to 1. So, you are getting a convergent sequence, all the sequence are convergent, but that sequence, if that sequence belongs to the class y, then we say the A transferred the element of from x to y, or A is the matrix transformation from A to y. Okay.
How do you denote it? A belongs to xy.
A belongs to xy. It means A take the element of x, first construct this series, and this should be convergent for each I, and then this sequence again take AX1, AX2, etc. form sequence, and that should be in the element of pi. Clear? So, the question is, under what condition on Aij this matrix transformations A maps from X to Y when X and Y are different. Suppose I take A matrix A, Aij transform L1 to L1. Then what should be the restriction on Aij, so that it can transfer each element L1 to L1. Similarly, what should be the restriction on Aij? Clear? If I say L infinity to L infinity, then what should be the restriction on Aij? If I say it transform from LP to LP, what should be the restriction? So, this transformation matrix A can be characterized. You can change the coefficient accordingly when we want the transformation from one space to other space. As soon as you change the space, the corresponding coefficient of the matrix will change, okay? And that gives you the characterization of the matrix required for transform. Suppose you are dealing with a problem where your domain is a space L1, but you wanted the elements should go to the L infinity, is it not? So, in that case, what type of the matrix you should use, so that it can transfer the element of L1 to L infinity. Clear? Similarly, if you have some range space, something is specified, but domain is something different, the corresponding matrix can be taken, can be chosen suitably, so that you get the curve. So, that gives you a very interesting thing, and in fact, I wanted to complete this verse. So, maybe next time we see that, okay, and that will be useful. Okay, thank you.